So we were doing resolution last time, and we was something about completeness, which we had to do. But okay, so today we'll essentially do. We'll also do Tableaux methods because we have already created huge foundations with propositional logic. The extensions to first order logic therefore are quite simple in these cases. But let's first before we get on to the Tableaux method, let's just go back to resolution because there is this issue of completeness. Yeah, so the resolution method basically tries to take as many clauses as possible with complementary pairs, and essentially there is the resolvent that you get by resolving two clauses Ci and Cj against some atom P, for which they have complementary pairs of literals, uses unification. So this is the resolution thing. So you take this set of clauses which have P as an atom and the set of clauses which have not P as an atom. The terms, the arguments may be different. So what you do is you choose this set and try to unify it. Find a most general unifier for some sets of these clauses containing complementary pairs, and having found the most general unifier, you essentially remove these clauses and you add this new resolvent Cij prime, which is obtained by applying that unifier and taking the union of these pairs of clauses. Yeah. Okay. So one of the things is that the resolvent Cij prime that is obtained by this kind of resolution is actually a logical consequence. That is something that we that is fairly easy to see. You can actually start with a model A, reinterpret sets of clauses in terms of the propositional connectives and the fact that they are implicitly universally closed, and you can do a case analysis and you will get this. Yeah. Okay. So that was one thing. If S prime is the set of clauses obtained by a single application of the resolution rule res1, then of course S prime is a logical consequence of S. So that follows from this lemma. And if the empty clause is derivable from a set S of clauses, then S is unsatisfiable, and this is what is known as a refutation, if you like. So one of the things that we proved was that, and this theorem for completeness of resolution refutation for ground clauses also holds for, I mean you can think of it as a proof of completeness of propositional resolution, because essentially we looked at ground terms in the predicates and there was no unification because everything was variable free, and we just took exact complementary pairs and did the resolution. Yeah. So this is like proposition. So res 0 here stands for propositional resolution. Yeah. So there is no substitution involved anywhere in this, and this is a theorem that we can prove essentially by looking at this measure. Okay. This measure, so you have a set G of ground clauses. Yeah. And the empty clause, if the empty clause is already in G, there is nothing to prove. Okay, so that means the entire set of clauses is essentially unsatisfiable. So if the empty clause is not in G, we consider this measure hash G. Okay, so this hash G is just the sum of the sizes of the clauses minus the number of clauses. So this n is the number of clauses, right? Okay. So now what happens is this measure is 0 if and only if every clause is made of a single literal. right. So now we will do induction on this measure hash g, and right. So one of the theorems we proved before our Herbrand's theorem was that G is unsatisfiable if and only if it contains a complementary pair, and so this resolution 0 will resolvent of a complementary pair will be the empty clause. Yeah. Okay, and we can go through this induction step, and I think we did this. Did we do this? Yeah. So I will not do this again. So this was essentially a proof that propositional resolution refutation is complete. I mean, refutation is what is complete. So this word refutation is important, the derivation of empty clause. So in particular, even though you take any set of clauses and you do a resolution and you get a new set of clauses S prime, even though this S prime is a logical consequence of S, there is no guarantee that resolution is complete for pure logical consequence. Okay? It is complete. So what this theorem tells us is that propositional resolution is complete for refutation whenever an empty clause is to be derived. So for pure logical consequence, by a direct proof through resolution, it is not clear that you can prove everything that you want to prove as logical consequence. What is clear is, you want to prove something as a logical consequence of a set of clauses, you negate it and add it to the set of clauses, and then there is a guaranteed derivation of an empty clause. So this theorem only shows that resolution is not a very useful, may not be a very useful thing if you want to do direct proofs. It is useful and complete only if you are looking at refutations. Okay, so that's an important observation, which for example, I mean there are some trivial examples one can give for to sort of illustrate this. So let's look at this. So let's look at propositional resolution. Okay, take this example. Okay, so take this biconditional. Yeah. So P biconditional Q, and here I am considering only propositions. Yeah. So there are so this P biconditional Q is equivalent to this. Okay, and which comes down to this set of clauses P comma not Q, not P comma Q, right? So supposing now I have a set of containing two clauses, and the two clauses have at least one pair of complementary pairs. Actually, they have two pairs of complementary pairs, but I do a resolution on one of them, then I will get the other pair as a single clause, and of course this clause is identically equivalent to the true, right? So all that we have been able to get by a direct proof is just that true is a logical consequence of this formula, right? I mean, so it is not clear that you can get anything else out of this, right? So on the other hand, so similarly, if you take the negation of this operator, which is essentially the exclusive OR operator, then also you just get true as a logical consequence. However, if you have a goal directed method, you want to prove specifically that P and Q, P is a logical consequence of P and Q, then what you do is you actually negate this consequence P, add it to the set of clauses, and then try to derive an empty clause. And for that, your propositional resolution is complete. So which means all proofs by resolution are essentially guaranteed only if they are indirect proofs. I mean, even only if you can prove the empty, derive the empty clause somehow, right. Okay, so, and in fact, the Tableaux methods are also very much like that. We'll come to that, but let me go back now to first order resolution. Yeah. So, okay. Okay, so essentially, so refutation is the only thing for which we can expect completeness, but then as we know from our original definitions, refutation is sufficient for proving anything. Anything that can be proven by a direct proof can also be proven by refutation, by contradiction. Yeah. So, in that sense, this is, so we will only look at refutations, but now given that propositional resolution refutation is complete, what happens to first order resolution refutation? That is what we are looking at. Okay. Here is some interesting thing. So, the main difference between the propositional case and the first order case is the presence of variables, the fact that propositions are that your predicates are parameterized on variables, and those, and the fact that you have a sigma algebra of terms which will act as parameters of the predicates, and different terms give you different predicates. Yeah. So let us look at this. Before I prove the completeness, I want this thing known as the Liftinglemma. Yeah. So what this does is, this is all too complicated. You can read it at your leisure. The more important thing is what this Liftinglemma says is essentially this. Supposing I have two clauses C1 and C2, and there is some and let us assume that these two clauses have no variables in common, okay. But that is okay. If I have two clauses, one of the things we can do is standardizing variables apart. So, we can rename all the variables, make them all unique. Yeah. So, there will be a set x1, a capital X1 of variables occurring in C1, and a disjoint set capital X2, which are the set of variables occurring in C2, and I perform some substitution, okay, and I perform two substitutions. So, essentially on the on C1 I perform a substitution theta 1, on C2 I perform a substitution theta 2, and clearly the domains of these two substitutions are going to be disjoint because the variables are disjoint. So, I am substituting disjoint sets of variables with disjoint sets of terms. Since the variables of C1 are distinct from the variables of C2, the terms in this substitution are also going to be disjoint from the terms in this substitution. So, the disjointness carries all the way up to here. Okay. So, that is what these two conditions specify, that the free variables of C1 are disjoint from the free variables of C2. The free variables of theta 1 C1 are also disjoint from the free variables of theta 2 C2. Okay. Supposing I guarantee these two conditions. Okay. If I can guarantee these two conditions, and then I can find a resolvent C prime 1 2 through some substitution, through some unifiers sigma. This sigma unifies theta 1 C1 and theta 2 C2. Basically what we are saying is, you find some atom P, you find complementary pairs P with some terms of x1 involving the variables of x1 occurring in theta 1 C1, not P, let us say, with variables from x2 occurring in theta 2 C2, and you are able to do a resolution, a single step of resolution, and you will obtain, let us say, a clause C prime 1 2, right. So, basically what we are saying is all the other the rest of C1 which was not involved in the resolution, the rest of C2 you will do the substitutions given in sigma. Now, since these two are disjoint, in their sets of variables. What this lemma just says is that it is possible for me to find a unifier row, okay, which will resolve these two clauses without doing the substitution. It will give me some C12, and it is possible for me to get the C prime 12 through another substitution tau. So, what we are saying is, having done these substitutions and then realizing that there are complementary pairs, and so there is a resolution step possible, is equivalent to finding a resolvent here, and then in order to get this I find an appropriate substitution tau. Yeah. Okay. So, what you are doing is you are lifting this resolution step to the one with variables in it. Notice that C1 and C2 have variables in them, right. I mean, whereas okay, in particular supposing here I have not made any assumptions about ground terms, but in particular we have to relate it to the completeness of resolution for ground terms, which is what we have proven before, right. We are going to use that in order to prove completeness. So, in particular if theta 1 and theta 2 are ground substitutions, then this sigma is essentially an identity substitution, right. I mean, because you are essentially doing propositional resolution here. Okay. So, this is equivalent, therefore, this can be lifted to doing a resolution on terms with variables and then doing a ground substitution tau to get C prime 1. Okay. So, what this essentially, if theta 1 and theta 2 are ground such that theta 1 C1 and theta 2 theta 2 are variable free, then you can do propositional resolution. But whenever that is possible, what you are also saying is it is possible to do a predicate logic resolution, a first order resolution, and get the same effect by doing an appropriate ground substitution tau. Right. So, this this is what this theorem says. Yeah, this is what this lemma says, and the proof of this lemma, I think I am going to leave it to you to study on your own. Yeah, it is an important lemma. You have to use the fact that these have disjoint sets of variables and these also have disjoint sets of variables, right. So, it is a fairly general purpose lemma, but we are going to use it only when in the case when theta 1 and theta 2 are ground substitutions. Yeah, that is enough for us to prove completeness of resolution refutation. Okay, by the way, so I can superpose those two figures. These two figures can be superposed to yield something like this. Yeah, yield a figure like this. So, a figure like this will represent the Liftinglemma basically. Yeah, right. So, now, so essentially the Liftinglemma helps us to use completeness of resolution refutation for ground clauses and lift it to clauses with variables in them. And by standardizing variables apart, we can guarantee those two conditions of the Liftinglemma are satisfied. And of course, any set of clauses represents a conjunction of the universal closure of each clause. One of the things we did was we showed that actually a set of clauses represents a universal closure of an AND of all the clauses, but that is equivalent to taking the universal closure of each clause separately. So, that will have a smaller number of variables and taking a conjunction of that, right. So, we will use basically these, right. So, the Liftinglemma guarantees therefore that if theta 1 and theta 2 are ground, then there exists corresponding ground substitution tau, which will produce the same effect as the Liftinglemma. We have Herbrand's theorem, which shows that a set phi is unsatisfiable if and only if there is a finite subset of ground instances of phi which is unsatisfiable, right. And so, what we do is to prove completeness of resolution refutation, we just consider only a finite set of ground clauses from which the empty clause may be derived. So, assume that okay, so let's go to the theorem. The theorem is just that suppose phi is a set of clauses which is unsatisfiable. There is no model, okay. Which means then what we are saying is that the empty clause can be derived in first order resolution, okay. And how are we going to do it? We are going to use Herbrand's theorem, and essentially what we are saying is that first of all we can standardize the variables apart, and by Herbrand's theorem basically what we are saying is that you can phi might be a finite or infinite set, I do not care, whatever it is, the ground instances of all those clauses is going to be infinite sets, right. But if phi is unsatisfiable, then by Herbrand's theorem there is a finite subset of ground clauses which are also unsatisfiable, okay. Now, if that finite set of ground clauses is unsatisfiable, we know from the completeness of resolution on ground clauses that the empty clause can be derived from them, right, ground clauses. Now, all that we need to do is take that finite set of ground clauses, I am calling them GCI, each of them has a parent in the original set phi through a ground substitution theta I, right. So, take only those clauses Ci and now apply the Liftinglemma. So, what you are saying is you take only that subset of clauses. So, there is a finite subset G which is refutation, which derives the empty clause completely ground. You take their parent clauses, all the Ci's, and the Liftinglemma guarantees that I can find a most general unifier and a resolvent. And the Liftinglemma guarantees all that provided I satisfy the disjointness conditions, which I can fulfill by standardizing variables apart, okay. And once we do that, essentially we can, by induction on the number of steps of ground resolution, for each step of ground resolution you can apply the Liftinglemma, okay. And I am not going to go through the details of that, but here is a simple illustration where there are two steps of resolution. So, the blue ones are all the ground ones, right, okay. So, you take, so let us assume that C prime 1 2 3 4 is the empty clause, yeah, and it is derived from these 4 clauses C1, C2, C3, C4. You take, let theta 1, theta 2, theta 3, theta 4 be ground instances of all these clauses. Then what you are saying is that there exists some resolvent sigma 1 2 between C1 and C2 here, there exists another resolvent sigma 3 4 between these two, that will give you C prime 1 2 and C prime 3 4, and there exists a sigma 1 2 3 4 which gives you, let us say, this C prime 1 2 3 4, which let us say is the empty clause. Now, the Liftinglemma in each case guarantees these red lines, right. So, it says that it is possible to find a resolvent C1 2 without doing any substitution, such that if I want C prime 1 2, then there is a ground substitution tau 1 2 which will give me that, and similarly in this case. And this, so look at this C1 2, C3 4, C prime 1 2, C prime 3 4 and C prime 1 2 3 4, they also satisfy conditions of the Liftinglemma. I can standardize the variables apart, right, and so I can apply the Liftinglemma again, and that guarantees that I can find a unifier, a most general unifier rho 1 2 3 4 and a ground substitution tau 1 2 3 4, which will give me my empty clause. So, from propositional resolution we can actually derive first order logic resolution, but only for refutations, right. So, the completeness is only for refutations, though it is clear that all the clauses that you get are actually logical consequences of the original sets of clauses. Yeah. Okay. So, so that means resolution is first order logic complete, and now some of the other things that we have to do is, first of all, we have to look at Tableaux methods, and we have to look at the completeness of Hilbert style proof systems. I think those are two important things that we have to do. We did propositional tableaux. Now, what about first order logic tableaux, right? In tableaux also, tableaux are similar to resolution in the sense that again you are trying to prove unsatisfiability. So, what happens? A tableau is a tree. We have these various Tableaux rules, right? Where are the Tableaux rules? Okay. We had these various Tableaux rules, right, which essentially give you a branching, with elongation and branching rules. So, this is an example of a branching rule, and this is another example of a branching rule, and these two are also branching rules. Yeah, this is an example of an elongation rule, and so is this. Yeah, and what we did was we just started with the set of clauses, kept on elongating as much as possible, and then if necessary. So, we broke down the clauses based on their syntax, on this structure of the syntax tree of the not clauses, of the formula. So, the important thing here is that in general, so the Tableaux method in principle, because it works on the root operator of the formula, is a bit like natural deduction, right. The natural deduction had introduction and elimination rules. The Tableaux just allows you to break the formula according to decompose the formula in terms of the root. So, it applies on the root operator, and so in that sense it is similar to natural deduction. But on the other hand, it is similar to resolution because basically unsatisfiability is what you prove, right. So, you are looking for a closed Tableau. Closed Tableau is a tree, is a Tableau tree in which all the paths are closed, and a path is closed if along the path you can get a complementary pair, right. So, if all paths have complementary pairs, then all paths are closed, and the Tableau cannot be extended any further basically. Yeah. So, as long as there is no complementary pair, the conjunction of all the formulas in a path is satisfiable, is assumed satisfiable. Okay. So, it is similar to resolution in the sense that you are going to look for finite tableaux which are closed, and the Tableau is closed if all the paths are closed. If even a single path is open, then the Tableau, then what you have got is an assignment, a satisfying assignment, right. Okay. So, one of the advantages that the Tableau had and continues to have for first order logic is really that resolution required a huge amount of initial paperwork to be done, right. You had to take these formulas, convert them into pre-next normal form, then take the formula, take the body of the pre-next normal form, convert it into conjunctive normal form, and that conjunctive normal form might often involve a distribution of or over and, which can expand the body, and in that sense there are certain natural disadvantages of resolution which are not which get hidden when we look at resolution only in terms of sets of clauses. So, if you are given only sets of clauses, then that is fine, resolution is fine, but otherwise there is you basically create through your pre-processing you create a mammoth formula. This is something that the Tableau does not require, because the Tableau does not require any of these transformations. It just naturally breaks up formulas according to their operators. Yeah. Okay. So it has these advantages over resolution, and since it works on the syntax of formula on the root operator, it is almost like natural deduction. Natural deduction has introduction and elimination rules for each operator, whereas Tableau keeps on breaking up operators, right. It just keeps on breaking up the formula based on the root operator. So, it has essentially only, so it uses essentially only the elimination rules of natural deduction, but it uses a branching, which a branching tree, and so otherwise it's a lot like natural deduction and it's a lot like resolution. It's like natural deduction because it's totally syntactic, and it decomposes formulas into in terms of their sub formulae. It's like resolution in the sense that you're looking for a closed tableau, you're looking for ways to close all the paths. Yeah. Okay. So, the Tableau rules, therefore, they are not surprising at all. We want to look for ways of breaking up each quantified formula, and you want to negations of quantified formula. That's how the Tableau works, right. So, we have two rules. Yeah, is there a question? So, there are two rules. So, and these two rules, there are these 4 rules, and these 4 rules are essentially like your universal quantifier elimination and existential quantifier elimination, because by De Morgan's law the negations are also duals, right, they dualize. So, you take this, so you have for all x phi, and basically what you are saying is that for all terms t, Tx phi is something that should follow from for all x phi. In the case of the existential quantifier, essentially the same restrictions hold as for existential quantifier elimination in the Hilbert cell proof system, right. So, there was a notion of a scope, creating a new and fresh constant. So, this A here is very much in that spirit. So, this A has to be a fresh constant which does not occur anywhere in the path, in that path in which you are doing this existential quantifier elimination. So, it should not have occurred before. So, this has to be fresh. So, I mean this is you remember these are these restrictions on existential elimination which we had for the Hilbert style system. So, in each this constant symbol A has to be absolutely fresh in that scope. In the case of a Tableau, the scope that we are talking about is the path which is open at the moment, which you are extending with something more, right. So, no parent along that path, no ancestor along that path should have had an occurrence of A if you are applying the this rule, right. The negation of the universal quantifier is very similar to the existential quantifier. So, the notion of a fresh A happens here too. I mean it's after all a dual, and the notion of, and this of course is models the same as the universal quantifier, right. In particular, when you are looking at it as the universal quantifier, this is for all terms t. I mean for every term t, this actually holds, right. What are we, in the case of when we did the Hilbert style proof system, it did not matter to us really. Notice that this is essentially for all terms t that are admissible in X. Whereas, if you are looking at refutations, which is what your Tableau does for closure, then if the Tableau path closes for one particular choice of the term t, it might close, it may not remain closed for all possible terms t, right. Because there is a combination of, there might be a combination of existentially quantified formulas and universally quantified formulas, because of which you might have to reuse this rule. We are not doing direct proofs, we are doing refutations. Actually, so let's look at an example. Okay. So this is what I am trying to say is that this for all and not there exists may have to be applied several times before unsatisfiability can be proven, and here is an example which illustrates that. Okay, take this set not of C is a constant. Let us assume that C is a constant in the signature. That is why I have not written it in red, I have written it in violet. I mean, let us assume C is part of sigma. Yeah. So I have not P of C, and F is a unary function symbol. I have P of F of Fc, and then I have for all x Px or not Pfx. Yeah. And now this set is unsatisfiable. Okay, and you can prove it by some other means, through unification, through resolution, whatever. But let us look at a Tableaux proof and what it involves, right. So, we just use elongation initially. So, we first list out all the so this is a tree, by the way. Yeah? I know it does not look much of a tree, but it is a tree. Okay. So, here this horizontal line is where the branching takes place, right. So, this P of C or not, okay, let us take this for all x P of x or not P f of x. Okay, I choose to instantiate this universally quantified formula with C for x, and if I choose to do that, then I get P of C or not P of f c. Okay. This OR requires a branching rule. So, you assume P of C and you assume not P of f c. Okay, but P of C of course contradicts this not P of C on the path, and so this path is closed. That is what this red square is supposed to indicate, that the path is closed. So, now you take this not P of f c, this path is open, right. Now, I do another instantiation of this for all, and this time I replace x with f of c. So, then I get P of f of c or not P of f of c, right. Okay. So, P of f c and not P of f c here are contradictory. Okay, this OR implies branching again, and this P of f c contradicts this not P of f c. So, this path closes, and this not P f of c contradicts this P f of c, and so this path is also closed. So, there is a difference here. In our propositional Tableaux method, we actually scored out any formula that had been used. All those formulae were, well, essentially disposable, if you like. Once you decompose the formula, you did not require the original formula. But here we see the first important difference. That is that a universal formula cannot be discarded after instantiation, right. It has to be reused. All other formulae can be discarded once they have served their purpose, once they have been decomposed. So, for example, once this branching has taken place, this P of C or not P of f c is useless and can be scored out. Okay. And similarly, this P of f c or not P of f f c can be discarded once I have done this branching, because they are essentially propositional. But all quantified formulae will have to be reused. Actually, what happens is that it is only for all x and not of there exists x, which are both only universally quantified formulae may have to be reused before you can prove your before you can prove that the entire tableau is closed. If this, supposing instead of not P of C, I had just P of C, right? Then what would happen is, this universal quantifier would essentially give you all, I mean, there would be an infinite path in the tableau would not close, okay. So if I were to take this set P of C, well, P of f of C, and for all x P of x or not P, oh, is this yeah, well, then some parts of the tableau will not close. But if you are looking at a complete tableau, then in that complete tableau you will essentially have to have all instances, all ground instances of this formula. That is like taking the entire Herbrand universe, and that is like elongating with an infinite number of formulae, right? But after all, your for all x is like an infinitary and, right? And your, if there is a constant, if there is at least one constant, then your Herbrand universe, the set of all ground terms that are possible, is an infinite set. So this essentially encodes an infinite possible path in the tableau, right? So now what here, so the only tableaus under quantification, under universal quantification or equivalently negation of existential quantification, the only finite tableaus are those which are closed. All the other tableaus, so for any set phi, so in the propositional case, because of the fact that we did pure decomposition and your formulas were essentially like toilet paper, right? Use once and throw away. Yeah. So you had only finite tableaus, and those finite tableaus could have, for a finite set of formula you had only a finite tableau, and it was always finitely branching, of course, and so you had only a finite number of paths. Some of those paths may have been closed, the other paths would have been open. But in the case of universal formulae, you have the possibility of actually having an infinite path, and this universal formula in an open in a tableau which is not, in which all paths are not closed, essentially encodes an infinitary path for all possible instances of that you can have for x. Yeah. Okay. Okay. There's I don't have any more slides, but but I can do some example. What is time now? Okay, there is one quick example I can do. One of the things that we did in if you remember, I don't know how well you remember, but there is a tendency for understanding to also be volatile. But there is something called slim tableau. Yeah, right. So there is this notion of, I mean, so a heuristic that you normally apply is that you postpone the application of branching rules as far as possible, and use elongation, give priorities to elongation rules. So, you first do all the elongation rules possible, and when the Tableau is got only branching rules possible, that is when you do branching. So, you get slim Tableaus because of that. In this particular case, this is essentially a huge elongation, if you like. So, it encodes a huge elongation. That is not a serious issue, but this huge elongation comes in the way of finding closure. I mean, after all, in what order are you going to put in all the do all the instantiations is a question. If you notice here, there was some guidance which this constant gave, right. So, if you were to take a proof like this, so let us take a refutation proof, because I want only a finite Tableau. So, let us take this simple thing, for all x p of x, no function symbols, 2 atomic predicate symbols unary, okay. One logical consequence of this is for all x p of x, and I am going to do an alpha renaming just to keep all the variables separate, right. I mean, it does not really matter, actually it does not matter at all, but anyway let us do this, yeah. Right. So, if you had to prove this, so clearly a Tableau proof for this would start with taking the set, this set, the set is going to be for all x px arrow qx, okay, and then the negation of this. So, that means not of for all x px arrow for all y qy, right. Okay. So, the negation rule essentially this is negation of arrow, right. I mean that, so there are those propositional Tableau rules, right. So, you take negation of arrow, so it elongates it. So, it elongates it to for all x p of x and not of for all y q of y, okay. And this thing, so this thing is essentially propositional, okay. So, essentially this can be discarded, yeah, okay, because we have now applied this elongation rule. Now, you have a question of how to proceed with this Tableau, and you have the choice of instantiating this universal quantifier, or this essentially existential quantifier. These two universal quantifiers provide no guidance at all. So, if you want a slim and finite Tableau, you have to first instantiate this, right. So, if you instantiate this, then what you get is essentially a fresh constant A. You are going to use a fresh constant A, and I am going to write it simply as not q of, this is also whiteboard mark. Okay, I'll use a green for the A. Yeah. So this is a new fresh constant, and this is what I would get, right? But of course, you can think of this as being disposable essentially, right? It is the equivalent. So the ones which are not disposable are the universally quantified ones, and therefore the negation of existential quantifiers. Yeah. Okay. So once you do this, this A gives you an guidance as to how you are going to initialize these two, right? And so essentially what you are going to do is you are going to get P of A here as one instantiation, and then you are going to get P of A, Q of A, arrow P of A, Q of A, right? Yeah, and then you are going to go through this. Now it becomes propositional. This will branch into essentially. Have I made a mistake? So this will branch essentially into not PA here and QA here, right? Okay, so now what happens is, okay, so this because of this and because of this, both the branches close. Yeah, and so you have a closed tableau. So this one, so in addition to the fact that you postpone branching as much as possible, it's not just slim tableau, it also ensures finiteness. If it is indeed unsatisfiable, the instantiation of existential quantifier and therefore also of not of the negation of the universal quantifier should be done first to provide an appropriate guidance as to what should be instantiation of the universal quantifier. Yeah. So it's I could have, of course, for example, I could have had here a formula like f of y or g of y, for instance. Supposing I had f of y or g of y somewhere, something like that, then this would give me not q of f of a. But then the instantiation I would have to do on this then would be of f of a for x rather than for a for x, right. So it gives me that guidance. That guidance has to be programmed, which is, notice that we do not have unification. So if you use the existential quantifier to give you the appropriate guidance, you can just take the terms from the existential quantifier instantiation and use them as substitutions for universal quantifiers and then do a propositional tableau. And so you get not only a slim tableau, you also get a not a guarantee, but a possibility of closing the tableau early. Yeah. Okay, so that is as far as tableau is concerned. I will do the tableau completeness and soundness tomorrow maybe, and I will stop here.